All right, let's talk about something really cool. How does an AI come up with a plan? I mean, not just any plan, but the absolute single best one possible. Let's get into it. Okay, picture this. A robot is stuck in a maze. Now, sure, it could just wander around randomly, or maybe try that old trick of always hugging the left wall, but are those really the fastest ways out? Probably not. See, we're not just looking for a path. We want the optimal path. So the real question is, how can an AI be totally, mathematically sure it's found the absolute best route? So the key to this whole thing, and this is a really big deal, hinges on one huge assumption. We have to assume our robot has a perfect map of the maze. I'm talking about knowing every single corridor, every dead end, all the rules of how it can move. In the world of AI, this is what's known as a planning problem, and it's the perfect setup for the technique we're going to break down today. And that technique? It's called dynamic programming. Honestly, it's a classic, a really foundational idea, not just in AI, but in fields like optimal control too. And it's exactly what we need to solve our little robot's problem.
Now, wait a minute. When you hear the word programming, you're probably thinking of writing computer code, right? Well, in this case, that's not what it means. It's actually an older, more mathematical term. Think of it as finding an optimal program of actions, or what we'd call a policy. At its heart, dynamic programming is a way of thinking. It's about tackling a huge, complicated problem by breaking it down and solving all the tiny little subproblems that it's made of first.
Okay, so for dynamic programming to actually work, the problem you're trying to solve needs to have two special properties. First up is something called optimal substructure. Sounds fancy, but all it means is that the best solution to the big problem is made up of the best solutions to its smaller parts. Think about it. If the fastest way to drive from New York to LA goes through Chicago, then your route from New York to Chicago must also be the fastest possible route, right? That's optimal substructure. The second thing you need is overlapping subproblems. This one's even simpler. It just means you end up solving the same little problems again and again. So instead of recalculating every time, you can just save the answer, cache it and look it up later. Super efficient. So how do we actually use this stuff to find the best plan? Well, the first step is actually kind of surprising. We're going to start with any old plan. I mean, it could be a genuinely terrible one. And our first job is just to figure out a way to give that plan a score. We need to grade it, or as we'll call it, evaluate it. So let's start with maybe the worst advice you could give our robot. Hey, just wander randomly. From any square, just pick a direction, whatever, doesn't matter. Our first mission then is to figure out precisely how bad this strategy is. And this whole process, this grading of our terrible plan, is called policy evaluation. Okay, so here's our maze, a nice, simple grid world. Those shaded squares, those are the goals. Now, at the very beginning, we have no idea how good or bad any of these squares are. So what do? We just give every single square a value of 0. Think of it as our starting point, our clean slate, iteration 0. All right, let's do one round of our evaluation. We're going to say that every step the robot takes costs 1 point, so it gets a reward of -1. After just one go around, what happens? Well, the value of every single square that isn't a goal immediately becomes -1. This is basically our one-step look ahead from that starting point of 0. Pretty straightforward, right? So we just keep doing this over and over again. And each time we do it, information kind of flows out from the goal, like ripples in a pond, updating the values of all the squares around it. After a while, the numbers just stop changing. They settle down, or what we call converge. And these final numbers, this is the magic. They tell us the true long-term value, or cost, of being in any square if our robot just keeps wandering randomly. So look at that top left corner. That -14 means that, on average, it'll take 14 steps to get to a goal from there. We have officially, mathematically, graded our terrible plan. Okay, so we've now proven with numbers what we already suspected. Our random plan is, well, it's not great. So what's the next logical question? Can we use this new information, these value numbers we just calculated, to actually come up with a better plan? The answer is absolutely we can. And that brings us to our first real complete algorithm here, policy iteration. And it's a really elegant little loop of evaluating and then improving. Policy iteration is pretty much exactly what its name suggests. It's a two-step loop that just repeats. Step 1, you evaluate your current plan, just like we did to get all those value numbers for each square. Step 2, you improve your plan. And how do you do that? You just look at the numbers, and from every single square, you pick the move that takes you to a neighboring square with a better score. You just act greedily. And this is a perfect look at that improvement step in action. On the left, you've got our old, go anywhere, random policy. But on the right, we use our value map to make a brand new, much better one. So take that square with the value -20. The new policy gives a clear instruction. Move towards the square that's worth -14. Why? Because -14 is a better score than -20. It means we're closer to our goal. We just do this for every single square on the board, and boom, we've got a new, way smarter policy. And that's the whole cycle, right there. You start with a policy, any policy. You evaluate it to find the values, then you improve it by acting greedily. And then you take that new, improved policy, and you evaluate it. Then you improve that one. You just keep repeating this loop. And here's the really amazing part. This simple process is mathematically guaranteed to find you the absolute, single best, optimal policy. No guesswork. So policy iteration is great. It totally works. But that evaluation step where we wait for the numbers to converge, well, that can take a really long time. So you have to wonder, is there a more direct route? A shortcut to the answer? Of course there is. And this shortcut is called value iteration. What it does is it kind of skips that whole two-step dance. Instead of fully evaluating a policy and then improving it, it basically smashes those two steps together. On every single update for every single square, it just asks, what's the absolute best move I could make from here right now? And it updates its value based on that one perfect look ahead. It just works directly on the numbers themselves until they represent the optimal path. So here's the key difference, right? You can think of policy iteration as this two-step dance. First, you figure out the values, then you figure out a new policy, then values, then policy, back and forth. Value iteration, on the other hand, just ignores the policy part of the dance. It just marches straight towards the optimal values. Once it has those final perfect values, the best policy just reveals itself. From any square, just move to your neighbor with the highest value. It gets to the exact same answer, but a lot of the time it gets there faster. Okay, let's take a step back for a second and look at the big picture. We've just seen these really powerful ways to find an optimal plan. But it is so important to understand where all of this fits inside the larger universe of AI. Because here's the thing, everything we've talked about so far, both policy iteration and value iteration, they only work because of that one huge assumption we made right at the start. Remember? Our robot was just given a perfect model of the world. It had the map from day one. And this difference is absolutely fundamental in AI. When you know the rules of the game, when you have the map, the problem you're solving is called planning. And for that, you use amazing tools like dynamic programming. But what happens when you don't have the map? When you have to learn how the world works just by trying things out through trial and error? Well, that problem is called reinforcement learning. And that requires a completely different and honestly fascinating set of tools. Yeah, these two situations, having the map versus not having the map, they really represent the two main ways we think about AI making decisions over time. Are you planning with a perfect model, like a chess computer that knows all the rules? Or are you learning from scratch, like a brand new robot that has to explore a building to figure out the layout? So let's do a quick recap of what we've covered. We started with this big idea, dynamic programming, which is all about breaking big problems into little ones. We saw how policy iteration works in that steady cycle. First, grade your plan, then make it better. Then we found a shortcut with value iteration, which just makes a beeline for the best values. But the single most important thing to remember, all of these amazing planning methods rely on one thing. You've got to have that perfect map of the world before you even start. And that brings us to the big final question, doesn't it? We've seen what an AI can do when you hand it a map. But what happens when you just drop it into a maze with no instructions, no model of the world, nothing? And it has to figure out not just the best path, but the map itself, just by wandering around and trying things. Well, that is the incredible challenge of true reinforcement learning.